In this problem, two coaxial conducting cylinders of same length and radii root 2r and 2r are kept as shown in the figure 1. The charge on the inner cylinder is Q, outer cylinder is inner cylinder is Q, outer cylinder is grounded. Inner cylinder charge is Q, outer cylinder is grounded. The annular region between the cylinders is filled with the middle part. Annular region, middle part of the cylinders is filled with material of dielectric constant K is equal to 5. So K is equal to 5. Smaller inner cylinder radius root 2 R and outer cylinder is 2R. Consider an imaginary plane of the same length L. See, this is the plane of the cylinder. To that plane, it is parallel to the plane of the axis of the cylinder. The cross-sectional view of the arrangement is shown in figure 2. Ignoring edge effects, the flux of the electric field to the plane is. So flux through this plane we have to calculate. So let us calculate. This diagram I have taken here. So solution. See here, this is the center of the circle. I will take O. This is R they have given. So I have drawn a, see first of this is the plane. So wherever the plane is cutting, I will take this is A, this is B, and this is C, and this is D, this is E. So AE is a plane which is parallel to the plane of this cylinder. Cylinder is downwards. See the upper portion we are seeing, right? The cross-sectional view from the above we are seeing. The plane is like this. This is the plane of the section, right? So about this plane, we have to calculate the electric field, flux of the electric field to the plane. How much electric flux is coming from this plane. So let us A, B, sorry I missed here, C, this is actually D, this is E, sorry, this is F. Wherever this plane is touching the cylinder surfaces, I have given a name. This is E. Okay. So AE is a plane parallel to the C, imaginary plane, same length L and distance R from common axis of the cylinder, right? The plane is parallel to the axis of the cylinder. So A, B, C, D, E, F, right? AF is a plane parallel to the axis of the cylinder. So inner cylinder is given Q. So outer cylinder charge is minus Q. Right? This is what given. Now we have to calculate the flux through this plane. So I will use Gauss theorem. By Gauss theorem, what Gauss theorem says? The flux enclosed in a Gaussian surface is Q times Q by 1 by epsilon times Q enclosed in it. This is the net charge. This is what the Gauss theorem says. Now, I will imagine this surface around the surface, I will imagine a Gaussian surface. See, this surface C and D, whatever the surface is C and D, is inside the conductor. Inside the conductor, the flux is equal to 0. So the flux due to CD, the flux coming out from CD, this one, CD, is equal to 0 because it is inside the metal. Now, inside the metal, flux is equal to 0. So, the CD linked with this one is 0. See, this O, A, B, C, DE and BC, this plane is enclosed in a Gaussian surface. So, CD and DE, this flux we can calculate at the center. Say, this is the plane. So, this is O. So, I will construct a small thing here. From here to surface, this distance is R, right, given. So, another is here. So, this surface also M. So, then what happened? This is R, this is root 2R. This is root 2R given. The radius of the smaller cylinder is root 2R and this is R given. Then what happened? This angle theta is equal to 1 by root 2. That means 45 degrees. This angle is 45 degrees. Actually, D is enclosed in the Gaussian surface. So, flux we have to calculate about ED only. See, this length, I will join this surface where this is the point of the surface. Then this is the radius of the, see, this is the radius of the bigger one. So this is given as 2R. This is 2R. So this is 2R and this is R. This is a right angle triangle. Which one? O. Here I am not given this point, and D. This is a right angle triangle. In this right angle triangle, this R, this distance is R, distance is 2R. So this angle, this total angle becomes 1 by 2, that is 60 degrees. Right? This is 60 degrees. So what is this angle now? This angle is 15 degrees. How? 60 minus 45 is equal to 15 degrees. Okay, now everything is ready. So we can calculate. See, the surface of the plane through which electric flux we have to calculate is making angle 15 degrees at the center. So, flux due to DE is equal to how much? This is the how much part? 15 degrees out of 360 degrees into, what is the formula? Gaussian surface, what is the flux linked with this closed surface? Then Q, net charge is Q here, plus Q is there, net charge is Q here, by epsilon naught. But in between, this is filled with a dielectric of constant K. So, K epsilon naught. Here also, if you see, same segment BC also makes the same angle at the center. So, this phi DE is equal to phi BC. So net flux is equal to the flux due to BC plus flux due to DE. So 2 into both are same. That's why I written 2 into 15 by 360 into Q by K epsilon naught. Actually, the minus Q will come here, right? This is outside. So this is the minus Q will come. But we are only calculating the magnitude. So minus I am omitting. So 2 ones, 2 eighteens, 180. 15 ones, 15 twelves. 15 twelves are 180. So how much we got? Q by 12 K epsilon naught. Right? So the net flux is equal to, right, the flux of the electric field to the plane. This plane, this portion only contributing. Q by 12 into K value given as 5. So 5 epsilon naught. So Q by 12 5s are 60 epsilon naught. So our answer is Q by 60 epsilon naught. That is the electric flux through the plane. This plane is outside. See, this plane is outside the Gaussian surface. This plane is inside the Gaussian surface. This is also inside. So whatever the flux linked with the DE is the same the flux linked with DC. That's why the total value is, let's check which answer is correct. Right. This is question number 2 in paper 2. So which answer is correct? Yes, Q by C option is correct. Q by 60 epsilon naught.